Okay, so last time we were talking some more bare bones, and I thought I'd show you guys something that will potentially become useful later. See if you can figure out how. Um, which is to say, we noticed that there was a lot of stuff missing in bare bones, right? So what was missing? Well, and for that matter, what was there? So let me just load the README that has sort of the list of what is there. These are the reserved keywords, right? Basically, these are the instructions in the language. And as we saw, there's some of them that always go together. So like, for example, to, you only ever use copy and to together. So that's really kind of one object, not, or one construction, not two. Um, and while, uh, and do kind of go together, and while not and do go together, right? So, okay, so there are a lot of things there, but there's also a lot of stuff not there. And you guys first pointed out that what's the a glaring omission is arithmetic, right? So there's no math there, um, except for the fact that we can add or take one away from a given variable. Okay. And as we saw, we could build addition out of this without too much trouble. And heck, we even built multiplication out of it without too much trouble, right? Because how can you think of multiplication? Yeah, just repeated addition, right? So if I wanted to do 5 times 3, then I could just do 5 plus 5 plus 5, right? Add it to itself, uh, well, 2 times, because you already start with one copy of it, right? Um, and there you go, right? So we can do multiplication, and well, it would require a little bit more work to think about how to implement it, but we could certainly do division too. We just have to think a little bit. Okay, so not horrible, but we could do it, because we could think of division in a couple of ways. Well, what's a natural way? You guys maybe didn't think about it this way when you were in school, like elementary school. Yeah, it's if multiplication is repeated addition, then division is really repeated subtraction in some sense, right? And then, yeah, you got to worry about, well, what do you do if there's a remainder and that sort of stuff. But right, we can do that. Um, so okay, great. And there is actually a very nice algorithm for doing this. Is called, well, Euclid's algorithm, or the division algorithm. So doing division is certainly possible in some sense. Um, Okay, we've got this while loop, which involves sort of a decision-making capability as to whether or not a variable is or is not zero. Okay, but what is missing, at least explicitly, is some sort of notion of if, right? So if something is true, then do something. Okay, there's no conditional expression here, and you might think, okay, that means we're hosed because, well, having a conditional is very important in basically every programming language. But what I want to convince you is that we actually do have it. We just have to build it out of some of the pieces that we've already got. Okay. All right. So to demonstrate this, let's make a new file, and I'll call it conditional.bb. Okay. And basically what I want to be able to do is something like the following. Okay, I'd like to have a construction that effectively does this. Okay, so if x is not zero, do something. Okay, and when I say do stuff there, that just take that as sort of a placeholder for a list of instructions that are bare bones instructions. It could be just one instruction, it could be like 5 million, right? But it's just some list of instructions, whatever it is. Okay, so I'd like to have something that does this. Okay, but I only have, hang on one second, the only thing that I have that's sort of capable right now of making a decision is the while loop construct, which would be something like while x not zero um, do stuff, and uh, end. Okay. Yes, Thomas. Okay, so if we take, so are you suggesting that we have this code and add this? Okay, you can't init with inside the while loop. Okay, but so you want to set x equal to 0. So if I can't init inside the loop, what could I do? Clear. Okay, all right, so let's think about what this is going to do, right? For sake of demonstration, let me do the following. Let me make another variable called in, and I'll just initialize it to 0, okay? And then inside the loop, and actually let me put some tabs in here so it's easier to read. Inside the loop, let's make our do stuff just to add 1 to in, okay? I need to do something, okay? And so I'll just do that because I need something, okay? So what would happen if I did not have this? Okay, it could go on forever, but under what circumstances would it do so? If x is not 0, okay? If x is 0, then what happens? We do absolutely nothing, okay? So, well, we've almost cracked it here, okay? So why is the clear x necessary? Okay, because if you do something and you clear x, what does that set x to be? 0. So then, is x not 0? No, now it is 0. Okay, so what this clear inside the loop does, this ensures that the loop body executes at most once. Okay, and I say at most once because could it execute 0 times? Yes, and under what circumstances would it do that? When x started as 0. Okay, and if x started as anything other than 0, then is x not 0? Yep. Increment in, clear x. Now x is 0. Is x not 0? Nope. So skip past. Okay. Does that make sense? All right. So let's save this and actually run it and make sure that I'm not full of it. All right. What did I call this? Conditionals.bb. Oh, and I didn't specify what x was. So if I set x equal to 0, what should be the ending value of n? 0. Okay, because I never actually incremented it. Okay, and is that what I see? Yep, okay. And if I set x to be anything other than 0, like 5, it only increments in once, and x gets reset to 0. Okay, so there we go. I've got an if construction. Yeah, that's pretty cool. Yeah, okay, excellent. Um, all right. So any kind of questions about what questions do we have about the bare bones stuff, just writ large? Because then we're going to start talking about the stuff that's going to make your heads explode. Huh? Terrifying. Okay. You know, I really should like make you guys like sign a waiver for what I'm about to do to you. Okay, intellectually. All right. So let me make a new file. And I will call this the X test or the X program, say. That's it. All it's going to be. Okay, so what's going to happen if I run this? Yeah, if x is 0, what happens? Absolutely nothing. It terminates and that's the end of it, right? If x starts as anything other than 0, then what's going to happen? Yeah, it's going to loop forever, right? And just keeps adding 1 to x, okay? Now, that actually begs the question, because I'm not sure how this is going to work. So if I feed this to, right, there it terminated, yes? What about if I feed it something else? So what's happening here? It's trying to calculate forever. Well, maybe. I mean, we don't know, right? But it's not finished, right? And we know that in some theoretical sense, it can never finish because can you keep adding 1 to a given number forever? Okay. Yes and no are both correct answers to that question. Why is yes a correct answer? Mathematically, is there a largest whole number? No, right? There is no biggest number. Computerly, like on a computer, there is, right? And this is one of the things that we saw, like when we were talking about overflow errors and stuff, is that computer arithmetic isn't precisely the same as so I just forced it to terminate. Computer arithmetic doesn't perfectly line up with human arithmetic. Mostly it does, but then there are those weird places when it doesn't, and that's where we get overflow and all of that stuff. Okay, so um, so if we think about this from the standpoint of not being bound by the limitations of my actual computer here, and think of it more in the realm of like Turing machine, like the tape could go on as long as I need it to, right? Then this program either runs forever or halts, okay? And under what circumstance does each thing happen? Under what circumstance does it run forever? If x is different than 0. And under what circumstance does it halt? If x equals 0, okay? Now, were we able to look at that program and determine that so really there are two pieces to this program, right? There's the program and there's the fact that I'm feeding an input of x equals something to it, right? Okay, so do you guys agree there's really two pieces here, the program and the value of x? Okay, so good, got that. So I just gave you guys this program and a value of x. For example, let's say there's the program. It's on the screen. X equals 0. What's going to happen? It terminates, right? You guys all looked at that and you processed it. You know, gears turned inside your head. Well, maybe not literally, but right. If you got gears inside your head, then you should probably see a medical professional, right? Um, okay, so you processed it and you came to the conclusion that it would terminate, right? And when we ran it through our little bare bones interpreter program, that confirmed exactly what we knew was going to be the case. Good? Okay, and you also were able to determine that if I gave you this program and any number that wasn't 0, that it would not terminate, it would go on forever. Okay, now our bare bones program, in some sense, or the interpreter, was not capable of making that decision. Because when I ran this thing, did it finish? No, but how do I know it's not going to finish next week? Just by running it. Maybe it'll keep going until next week and terminate. Maybe it'll keep going until the sun explodes. I don't know, right? So, but were we as humans able to look at this and determine that for x equaling, say, 1, this would not terminate? We don't need to run it to find that out, right? We can just read it and know that. Okay, so this gets us to the big question, okay, which is the limits of, essentially the limits of computation. What can't we ever do, no matter how fancy pants of a computer we got? Okay, so the halting problem, okay, which is, you guys remember when we started talking about Turing machines last week, and I actually showed you guys Turing's original paper, right? And it was on computable, blah, 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 with an application to the Entscheidungs problem. So I've had to really practice pronouncing that, and I'm sure I'm still butchering it. But okay, so what is the Entscheidungs problem? Ich bin ein Berliner? No. See, the key to a good comedy routine is that you go back to earlier points in the comedy. Yeah, okay. See what I did there? Yeah, okay. So, right. So the decision problem uh, basically is something that came out of mathematical logic, okay? And it came out of um, kind of an interesting place. Um, so let's kind of go back into history for just a moment, okay? And in fact, I want to use the iPad to demonstrate something real quick here. How many of you guys have ever heard of a guy named Euclid? Yeah, you've heard of Euclid. Who was he? Uh-huh. Mathematician, good. Uh-huh. Geometry, good. What about when did he live roughly? No idea? Yeah, ancient Greece, although he actually lived and worked in Alexandria, in Egypt. But at that point, it was, uh, well, it wasn't part of Greece, but it was Greeks ruled it. Okay, so, um, all right, here's like 100 years of Greek history in 10 seconds. Alexander the Great conquers a whole bunch of crap, right? Then what happens? He just up and dies. So what do all of his generals promptly do? They promptly go to war with each other and carve up what's left of what he had conquered and into little fiefdoms, right? And Egypt became one of them, by that was taken over by one of his generals, whose name was Ptolemy. Okay, so there was a period basically of Greek rule of Egypt under the Ptolemaic dynasty. They basically took over as um, the pharaohs, okay, basically until the whole shindig went down with Cleopatra. She was part of that line, by the way. She was the last one because she had the thing with Mark Antony and then Caesar and a civil war, and eventually it becomes a Roman province. Okay, so for a few hundred years, it was essentially Greek ruled territory. And the second Ptolemy um, basically established Alexandria. Well, you kind of know where it gets the name, right? Um, and really fostered it as a center of learning in the ancient world. Okay, and so Euclid and a lot of other mathematicians of the day hung out in Alexandria, and that's where they did their thing. Okay, so um, if we go back to Euclid, and we're talking about 300 BCE here, okay, was when sort of Euclid, roughly speaking, flourished. Um, so one of the things in Euclidean geometry, and I'm not gonna state it the exact way that Euclid did for reasons that'll be, well, I'm not gonna make them clear, but it'll make it easier to have the discussion. I'm gonna state something that's equivalent to it. All right, so I'm gonna have a line, and I've got a point that's not on that line, right? How many parallel lines can you draw through that point to that line? Precisely one, right? Okay. Um, so Euclid has, at the very beginning of one of his books called The Elements, a list of uh, basically starting assumptions, definitions, starting assumptions. And one of the assumptions, it's called the fifth postulate, is not exactly what I said here, but it's equivalent to what I just said here. What I've actually stated here is called Playfair's axiom, but like I said, it's equivalent, so we'll just run with it. And the other four postulates are pretty straightforward, right? That if you add equal things to equal things, the results themselves then are equal. Well, that seems pretty reasonable, right? But then there's this fifth postulate, okay? And this really bothered mathematicians back then because they thought, we ought to be able to prove this from the other things that we already have, okay? And thus began several thousand years of people trying to prove this, called the parallel postulate, from all the other pieces. There's just one problem, okay? What you said, that there is exactly one line, it's only true if we're on the plane, okay? So I can't really draw this very well, but I'll make a stab at it. We draw a sphere, okay? Not the best sphere in the world, but you guys get the idea, okay? And straight lines on a sphere are by definition arcs of what we call great circles, okay? So what's a great circle on the sphere? The best example of one is the equator, right? It's a circle that has the same radius as the sphere. Okay, what would be another great circle on, say, the Earth as a sphere? Huh? Those are not, yeah, okay, good. Those are not great circles because their radius is actually a little smaller than that, the equator. Okay, so Tropic of Cancer, Tropic of Capricorn, okay? All the meridians, yes. Okay, so the prime meridian, which goes through Greenwich, England, right? But any of the longitude lines that go both through the North and the South Pole are also great circles, okay? If we pretend for the moment that the Earth is a perfect sphere, it's actually not, but let's just pretend it is, okay? Then the radius of those circles is exactly that of the sphere, okay? And there's no reason that they have to go this way or that way, right? You could imagine sort of tilting the Earth or whatever, or tilting the lines, sort of rotating them around and getting all kinds of great circles all over the thing, okay? So a straight line on a sphere is a segment of one of those, okay? So, for example, let me just highlight here the equator, okay? And let me just imagine, well, any segment on it, okay? Doesn't matter, right? So, um, if I pick any other point, okay, and I want to ask how many lines, which is to say great circles or segments thereof, uh, of are there that go through that point and are parallel to the orange circle? None. Okay. And now here, what does parallel mean? Not intersecting, right? So we called in the planar case up above, we called that parallel, okay, meaning that those two lines never intersected. Okay. In fact, the word parallel is not shockingly Greek. It literally is para alelois. So it means laying beside one another. Okay. Okay. So, but can you guys see that there's no way I can draw a great circle through the green dot that's not going to intersect the orange circle? Yeah. Okay. So what does that mean? The parallel postulate is different on the sphere than it is on the plane. Okay, which means that any attempt to prove the parallel postulate is sort of doomed to failure because you could have two different versions of it and have perfectly good geometric systems, right? We can do geometry on the sphere, works great. We can do geometry in the plane, also works great, right? So somehow the parallel postulate is, you can't prove it from all the other things because it's somehow outside of those other things. Okay. Okay. So now what does this have to do with computer science? Well, like I said, flash forward several thousand years, and it wasn't until much later that people realized this exact point that you can't prove the parallel postulate because there are actually three different versions of it that give you perfectly good geometric systems. There's the Euclidean version, there's the spherical version, and then there's a weirdo one called the hyperbolic version, where you need to smoke a little something before you do that. Okay. All right. Uh, so this idea of being able to understand a logical system and what is sort of included or not included took several thousand years to stumble on, A, and B, and this is where the 20th century sort of comes in, to really codify, well, what does it mean to have a logical system and what does it mean to be able to prove things within that system? Okay. This is the time period, of course, during which Turing is doing his studies. Okay. So Turing is very well versed in what's going on in mathematical logic at the time. Okay. And the Entscheidungsproblem uh, and this idea of a complete system of logic was very much at the cutting edge of mathematical research at that point, right? So in the first 30, 40 years of the 20th century. Okay, so the halting problem. Okay, let's get to it. So let me go back to the pie for a moment. You were able to determine if this program terminated or didn't if I gave you this program and a value of x, right? So I gave you a program and a number. Good? Well, congratulations. You guys are all just fancy Turing machines. Okay? Sorry, but you're a Turing machine. Okay? But this is just one program, right? It's a very simple program, right? What about if I wrote some other program and handed it to you? You think you'd be able to go through it and figure out if it terminated or not? Yeah, it depends on the complexity of the program. But if I just give you a program, even if it's a million lines long and super confusing, okay, if you are really diligent and good, right, and have plenty of time, could you go through and figure out whether or not it would terminate? You could. Okay. So doing this for a specific program is nothing special. I want to change the question. If I give you any program, can you determine whether or not it halts? Okay. Well, okay, but see, here's the thing. If I give you a specific program, could you do that with sufficient time and skill? Okay. But what about if I give you literally any program that is theoretically possible? And I want to know whether you can decide for every program that could possibly exist whether or not it halts or not. Okay. Now, that's a different question. Partly you could say, well, of course not, because there are infinitely many programs, and so I could never actually finish that, right? But what I want to convince you of is that it's not actually possible to do that, okay? And so let me substitute for you as the human. Well, could I write a program that could determine that this program halts, right? If you guys were able to do it by reading it, then I ought to be able to write a program that could figure that out also, right? Because, like I said, you guys are just Turing machines. I mean, I hate to belittle you here, but sorry, right? I'm a Turing plus. No, I'm kidding. There is no such thing. Okay. All right. So you could look at a specific program and figure it out, and hence there might be a program that could figure out if this program terminates or not. Okay. And maybe if I have a really, really nasty program, you could figure it out, which is to say, another program could figure it out. But what I want to know is there a program that can do this for any program? Okay, so that's a different question. Okay, so let me go back to the iPad and kind of sketch out what I mean here. Okay, so is there a program we'll call this program capital H, that when given another program P and an input X determines if P terminates with input X. Okay, so this is the question. Is there such a thing? Okay, what do you guys think? No. Okay. So there is no such program H. We're going to prove it today. Okay, so in order to prove this, we're going to do a gambit that mathematicians like to do, which is called a proof by contradiction. Okay, so let's say I want to prove that H cannot exist. Assume it does exist. Let's assume that there is a program H that can do this. Okay, then we'll play with H and we'll do some stuff. And if that leads us to bullshit, okay, which is to say a logical contradiction, then what are we forced to conclude? That our original assumption that H existed was itself bullshit, therefore H does not exist. Okay, so that's the game we're going to play. Okay, so assume that H exists. Okay, now we talk for a moment. How can I give a program to another program? What does that mean? Well, here's where we can be really brilliant. Okay, so let me go back to the pie for just a second. Okay, so I have here a program. It doesn't have to be this one. It could be one of the other ones that we wrote earlier, yesterday or whatever. But here's a program, right? How can I feed this as a thing to another program? What I want to claim is that a program really is just a big number. Okay? So one way to see that is just to say, well, actually, hang on. There's a, oops. What's the symbol for this? Format, canonical. Okay. I want this. What was it called? X test. Okay, so there we go, right? There's my program, and you guys can even read it over here on the right, right? I have some comments, right, which I could delete. They're obviously not necessary, but I've got all of the different words that make up the thing, and then there in the sort of middle part, what is all those? That's just a crap load of numbers, but what are they? They're hex, right? It's expressed in hex, but they didn't just come out of thin air. Like, why are those numbers there, right? So, for example, the very first one is 2-3 hex. What is that? Yeah, it's the ASCII encoding of the hashtag, right? And what about 20? Well, that's the ASCII encoding of space, and 54 is the capital T, and so on and so on and so on, right? So I could, for example, encode the program as just a big number, right? So the program is just a number. It's a really long number, but it's a really long number that's just its ASCII encoding, for example. Yeah? Okay. That point is going to be key later. Okay? All right, so back to the iPad. So feeding a program to another program just means take the program that you want to feed, think of it as a big number, and, well, feed it on in. Okay? So what I have here is, and let's sort of think of this as a big black box, is H. Okay? And I feed into it a program and a value of X, okay, which is just a number of some sort. Okay? And what it's going to feed out is a 1 Oops, sorry. That's not what I meant to say. And let me just write it, not program. Let me just call it P. Okay, good. So I'll take this as it will output either a 1 or a 0. Okay, it'll output a 1 if it does terminate and a 0 if it does not. Sound good? Yeah? Okay. Um, okay, this is really unfortunate that I've used X here in two different ways. Um, you know what? Do you guys mind if I call this the Y machine? So I typed it on the computer using X, but could I just change the X to a Y? Is that okay? Okay. That way I'm not using X in two different ways. Okay. So our Y machine was while Y not 0 do increment Y end, right? So that was if Y is 0, what happens? It terminates, nothing, it's done. If Y is not 0, then it continues, okay? So this is my Y machine, and I feed into this a number Y, right? And as we saw, if Y is 0, it terminates, and if Y is non-zero, it goes on forever, okay? And it doesn't output anything, but it either goes on forever or it doesn't. Okay, does that make sense? Yeah? Okay, now, I got two machines here, or two programs, right? Could I bolt them together? Could I take the output from one as the input from the next? Sure. Okay, so I'm going to make a new machine, okay, which we could call H++. We can call it whatever we want, right? And inside, it's going to take in two things. It's going to take in a P, it's going to take in an X. It has the H machine inside. Those inputs go here. It outputs as either a 0 or a 1 that goes to our Y machine. Okay? Okay, good. All right. So there's a machine, right? H processes it, comes up with some sort of output, gives it to Y. There we go. Okay, now here's where it's going to get crazy. Is H++ a program? It is, right? So it's just a big number, right? So what I'm going to do, so I've got, let me just sort of draw it smaller here. H++ is a program, which means I can feed it to itself because it's a program. And as a number, I can feed it to itself. So I'm basically going to ask, what happens when H++ processes itself? Okay, this is where the contradiction will come. Okay, so to explain this better, okay, I'm actually going to switch gears and I'm going to let somebody else explain it. Okay, which is to say, we're going to use some YouTube here. Okay. Um, Okay, so let me switch the output of the audio to this. And then I need to turn on Mac and switch to that. Let me put this over here and put it in theater mode. And then I need to turn on the audio. And then I need to turn the audio on over here.
Is it just the fact that, like, because it doesn't make sense, because the H++ needs that initial code, so if you feed it into itself, it doesn't have that?
Well, it does, right? Because think of it, H++ is a giant program, which is to say its code is just some big old number. Well, I can take that number and feed it to this program, okay? And what's clever here is I'm feeding it to it both as the program and as the number. Right, so I'm sort of double feeding it in some sense, okay? All right, so how many of you guys have ever seen or heard of either number file or computer file on YouTube? Yeah? Okay, so, it's a series of YouTube videos. They're pretty high quality, generally speaking, okay? And they have a really good knack for explaining interesting things. Well, and also they do interviews with famous computer people, right? So a lot of really good stuff here. But let's look at their video.
Today we're going to be talking about a problem
Can you guys hear it coming out of the cans? No, because it's coming out of my monitor. But all right, let me adjust the volume down on here. Okay, roll.
logic and how
There
in
we go.
solving that problem.
Is that loud enough but not too loud? Okay.
Today we're going to be talking about a problem in logic and how in solving that problem, Alan Turing almost inadvertently invented the modern digital computer. So we start back at the beginning of the 20th century, where mathematicians had posed this problem. In logic, we're interested in finding, do these premises entail this conclusion? So premises are the bits you start off with in an argument. They are the bits you know at the beginning or your assumptions. And the conclusion is the bit you want to establish, the bit that you reason to with your argument. And we want to know, is there a test that will tell us, yes, for sure, these premises do or don't entail this conclusion? Is there an automatic way of finding out whether they do or whether they don't? So that's the problem. It's called the decision problem. And mathematicians wanted to find out, is there an answer to the decision problem for first order logic? That's the kind of logic you learn in philosophy or mathematics at university. So lots of mathematicians were trying to work out, is first order logic decidable? That is, can we automatically test whether the premises entail a conclusion? Alan Turing was one of the first to discover that first order logic isn't decidable. To prove this, it's really difficult conceptually because you have to be able to show no possible program